Stanford University.
Okay, hi everyone. So back with lecture 14. So in today's lecture, what I'm going to do is introduce really the last sort of major architecture for neural networks that we're going to teach you in this class. And so that's going to extend beyond what we've seen with both recurrent neural networks and convolutional neural networks. And today what I'm going to start to look at is having tree-structured recursive neural networks. So this is a topic that is very dear to both me and Richard. It's sort of dear to me as a linguist because I sort of believe that languages have this basic tree structure, as I'll explain in the coming minutes. And it's dear to Richard because it's what his thesis was about, as we'll talk about some of that work later on. So there's some new stuff here. There's some stuff that in some sense is the same. So we kind of adopted the name recursive neural networks to refer to tree-structured neural networks. But if you think about it, recursive and recurrent are kind of sort of come from the same Latin root, and they're exactly the same through the first 5 letters. And so, I mean, in some sense, it's kind of a form of recurrent network, but it's now done over tree topology, as I'll explain. And so more recently, people have commonly referred to them as Tree RNNs, sort of emphasizing that more what's different is the geometry of what you're dealing with. And in the course of that, I'll talk also a bit about constituency parsing. So that's the sort of, so I'll start off with some of the motivations and looking at how these kind of models can be used for parsing. We'll have the research highlight, and then I'll go on with some other stuff with some more applications and looking at some of the sort of better architectures that you can then build for tree recursive neural networks. Before getting underway, just quickly, reminders. So there are some staffing complications coming up. So for Richard, he's going to be away on Tuesday, so his office hours are going to be after class on Thursday, so come along then to talk to Richard. Conversely for me, I also have a couple of irregularities in my schedule. So for tomorrow, for the sort of the morning SCPD slot, there's a linguistics faculty meeting, so I'm going to have to move that earlier to 9 to 10. The afternoon will be the same as usual for project office hours. But then next week, I'm going to be away at the end of the week, Thursday and Friday. So I'm going to have to sort of reschedule that, and I'm going to move the afternoon slot till the following Monday. So look on the calendar and get straight when those times are. But we do still really want people coming and chatting to us and the various other final project TAs about their projects. Assignment 4, make sure you're getting something working using a GPU for our milestone. We're seeing a lot more people using GPUs, and that is great. Any problems, stop by one of the TA's office hours or coding sessions and get those, or send Piazza messages and get that sorted out. And then just in general for final project discussions, please come and talk to us about your projects. And we sort of regard it as just really, really important for the final project that you actually have something that you can run by the end of this week. That, you know, if you're we hope everyone doing a final project is in the position where they have some data ready to go and they can run some kind of baseline this week, because, you know, if you aren't in that position, it's sort of pretty marginal as to whether things could possibly come to a good conclusion given the time available. Any questions about that? Talk to your project mentor. Okay, let me go on. So I just thought I'd start with some general remarks about sort of what kind of structures that we put on language when in some of these NLP and deep learning applications. This is just a fun picture for the sake of it, but over at CMU, they actually have this lovely artwork, which is the bag of words. And you have the bag with words inside it, and down onto the floor here have fallen the function words that are outside the bag of words. So one model of language that ends up being used quite a bit in deep learning and is sometimes very effective, as we've discussed, is you have nothing more than a bag of words. And for some kind of semantic similarity kind of objectives, I mean, the sad truth is that our state of the art isn't really beyond a bag of words, so that people have used clever bag of words models, things like deep averaging networks, and get very good results. So like there were papers at last year's ICLR. So ICLR is this new conference where a lot of deep learning work appears, the International Conference on Learning Representations. And so there was a paper last year from people at the Toyota Technical Institute where essentially their result was that for doing paraphrase detection, whether things have roughly the same meaning, that they could get better results with a sort of deep averaging network of a sort than people had been able to get with any kind of more complex structured neural model. I think that's a sad result, not a good result, but that's the current state of the art. On the other hand, in linguistics, and in some computational models, people attempt to use very elaborated structures of language which capture a huge amount of detail. And so you can be at either of those extremes, or you can hope to be somewhere in the middle. And if you want to be somewhere in the middle and have something that sort of roughly captures what are the most fundamental properties of language, it seems like you don't want to have word vectors, and you want to have something that can minimally capture the sort of main ideas of the semantic interpretation of language. And the idea I want to get at there is it seems like the fundamental notion for human languages is that we have this idea of composition where we can put together the meaning of phrases. And so we'd like to know about larger units that are similar in meaning. So if we have two pieces of text, perhaps for a paraphrase example, the snowboarder is leaping over a mogul, or a person on a snowboard jumps into the air, it sort of seems like the first essential point that a human being would notice and think as part of the solution here is that person on a snowboard means roughly the same as snowboarder, that it's a paraphrase. And we can do that because we can take the sequence of words, person on a snowboard, and say, that's a phrase, and we can put together a meaning for that phrase, even if we haven't heard it before, and know that it's kind of got this meaning that's roughly the same as snowboarder. And so essentially that's what human beings do every day when they're listening to their friends, right? You know, that every day people are saying to you different sentences. You know, they might first off just say, how's it going? And you've heard that 10,000 times before. But as soon as they get a bit further into describing their day, they're going to be saying sentences that you've never heard before, and yet we can work out what they say, and we're not working out what they say just as a bag of words of saying, this is about a party. We're actually getting the details of what they said and who said what to who, and we're doing that by starting off by knowing the meanings of words and then doing a semantic composition where we can put smaller units into bigger units and work out their meaning. And so we'd like to have models that could do the same. So at the very top level, this is compositionality, as to how you can put pieces together into bigger parts and then understand what those bigger parts do. I think it's a problem that's especially prominent when you start thinking about human languages. But I'd like to suggest it's not only a problem that has to do with human languages. In many ways, it's sort of a more general cognitive capability, so that if you have something like a complex picture, well, that's also something that has a compositional structure, so that you have pieces of stuff, that you have parts of a church that go together, you have people that go together into a crowd who are in front of this church, and that also has a kind of a compositional structure. So that in general it seems that for language understanding in particular, but also for other kinds of artificial intelligence, that we need to have models that have this kind of capability for semantic compositionality. You can put together smaller pieces into larger pieces and work out the meaning of those larger pieces. And what I'd like to suggest is our tree recursive neural networks are one model that you could think about as a good model for understanding compositionality. So there's this general idea of sort of taking parts and putting them together into bigger parts and understanding their meaning. There's a notion that's related to that which goes slightly beyond that, which is the notion of recursion. So by far the most famous linguist is Noam Chomsky, and so in some of Noam Chomsky's recent work with colleagues, they've tried to advance this picture that in terms of it's for 50 years it's been Chomsky's position that humans have this special innate born with part of your brain structure, ability for human language that sort of sets us apart from other beings, and that's sort of actually seeing that as having sort of specific brain structure for language. Not everyone else believes that, but they've been trying to sort of put forward these proposals as to what is special in the sort of capabilities for humans for language. And Chomsky and colleagues have wanted to claim that really the defining property is that humans have this ability, which you see through language, to have recursion. So that's just like in your CS class, right? When you have things going back and back to the same thing, looping over, that you have recursive structure. And that human languages have this kind of recursive structure, it appears. So what's the idea of that? That if you have the man from the company that you spoke with about the project yesterday, that what we have here, I think I might have, oh no, that's great. What we have here is sort of recursive levels of the same kind of structure. So the project is a little noun phrase. The company that you spoke with about the project yesterday, that's a bigger noun phrase that contains the smaller noun phrase, the project. And then the man from the company that you spoke with about the project yesterday, that's an even bigger noun phrase that contains my other two noun phrases. So human languages have this nesting of structure where you have the sort of same units like noun phrases and clauses that will nest inside each other, and you can nest them deeper and deeper. And that gives us the idea that recursion is a natural thing for describing human languages. And that's essentially the sort of basis of Chomsky's claim. Now, are human languages recursive? I mean, cognitively, that's actually a little bit debatable, and there are active debates on psycholinguistics and this kind of issue. I mean, it's sort of complex because, really, as soon as you're thinking sentences are only going to be some finite length, no one's going to say a sentence longer than 300 words, you can never sort of prove that things are fully recursive because there's sort of a maximum depth as to which things are going to be embedded. And there's slightly more to it than that. It's a well-known psycholinguistic observation that actually having things embedding in the middle of the sentence, so I sort of deliberately put the project not right at the very right edge, but had something come after it. So when you're sort of having more central embedding, that tends to be disfavored in human languages. So although you get a lot of embedding, most of the embedding that you get tends to have more of a chaining structure where you have a right branching kind of structure. And to the extent that structure is purely chaining, then you don't actually need to have full recursion to describe it because you can think of it more as a kind of an iterative sequence. So anyway, some cognitive arguments there, cognitive science arguments, but nevertheless, if you're sort of wanting to give a neat sort of natural description of natural languages. It's sort of basically you end up describing them recursively, because what you want to say is, well, there are noun phrases which can expand to various things, like a short noun phrase like the man followed by a prepositional phrase which has a preposition from followed by a noun phrase, and here's this big noun phrase, and inside this noun phrase it's got a relative clause, and inside that it's got other noun phrases like you and the project. So you kind of get these levels inside each other heading down recursively, and you can, and indeed people do in things like newswire sentences, embed them even more deeply than my example. And so thinking about these kind of tree structures would have embedding inside them, where we can have noun phrases with noun phrases inside them, are sort of a natural way to think about language structure and to think about things like how we disambiguate sentences. We sort of talked before about having ambiguities of attachment, and we talked about dependencies before. The other way to draw these and think about them is to have these kind of constituency or phrase structure representations, which in computer science terms correspond to context-free grammar representations. And then we have noun phrase units, and we can be either saying that with a spoon is modifying the verb eats, it's a child of the verb phrase constituent, or the with meat here is a similar prepositional phrase with a noun phrase inside it, but it's modifying the noun phrase spaghetti to build a bigger noun phrase. And so as soon as we're sort of using these kind of structures in a context-free grammar kind of structure, we have the ability for recursion, and human languages seem to indicate that. And we kind of want to refer to these units when we do other tasks. So next Tuesday, I'm going to talk about coreference resolution, which is how you refer back in the text or to the environment to refer back to entities that have already been established. And that sort of can be thought of as sort of picking out pieces of structure in terms of this kind of constituency compositionality. So John and Jane went to a big festival. They enjoyed the trip and the music there. So they refers back to something, and it seems to refer back to this noun phrase, John and Jane. Enjoyed the trip, so the trip's a noun phrase which seems to refer back to going to a big festival, and then and the music there, the there is again referring to this big festival. Okay, so and finally, having these kind of grammatical analyses of sentences is clearly better for some tasks. That it's capturing a very powerful prior of what human language structure is like, and is then sort of useful for understanding and interpreting human languages. So, you know, at the start of the course, we just had word vectors, and so we had word vectors for things like Germany, France, Monday and Tuesday, and we sort of were able to capture word semantic similarity in terms of our word vectors. What we'd like to be able to do is say, no, as well as just single words, we have larger constituents. So we have noun phrases like the country of my birth or the place where I was born. And we'd also like to understand the semantic similarity between those phrases. And the idea that we're going to develop to answer how can we do that is that what we're going to do is say, well, what we'd like to be able to do is take bigger units of linguistic structure and also work out how to calculate their meaning as vectors and place them in exactly the same vector space. So we're sort of hoping we can take bigger phrases and say, let's just stick those into our vector space as well, and also represent their semantic similarity as a kind of vector similarity, where of course this example is only two-dimensional, and in practice we'll be using 100, 200, 1,000 dimensions. Yes, question? Okay, so the question is, why would we want to put them in the same space as the word vectors? I mean, that's not a necessary thing. Obviously, you could say, no, that's just not what I want to do. I'm going to have word vectors in one place and phrase vectors in another place. The reason why a lot of the time that seems a good idea is that, I mean, individual words can capture a lot of meaning, and in particular they can sort of bundle up a bunch of semantics that's often equivalent to things that you can say in other ways with a phrase, right? So I guess I had the example right at the beginning where I had, you know, person on a snowboard and snowboarder, that it seems like, well, those should be counted as paraphrases and mean the same thing. And I'm only going to be easily able to capture that kind of similarity if I'm using the same vector space to represent both phrase meaning and word meaning. Okay, so that's our goal. And so the question is, how can we go about doing that? And, you know, for words, what we did was had a big lexicon of words and said, let's learn a meaning representation for each one of them, and we were able to do that. I mean, that's clearly not possible for phrases like the place where I was born, because we just have an infinite number of such phrases as they get longer, and so we can't possibly calculate and store a vector for each phrase. And, you know, as we started to see last week, is even for words, in a lot of cases, it seems like it might actually turn out to be sort of unappealing to store a vector for every word, especially when they're words that have some morphological complexity, like snowboarder, which is, you know, snowboard. And so we started to talk about even words, how we might want to compose their meaning out of smaller units as part of some neural network. So again, that's what we're going to want to do for having these bigger phrases in language. So we're going to have something like the country of my birth, and what we'd like to be able to do is semantic composition. We'd like to be able to use the principle of compositionality, which is sort of a famous thing from philosophy of language or semantics, which is saying you can derive the meaning of a phrase or a sentence by starting with the meaning of its words and have some kind of then composition function that you can then calculate meanings of bigger units as you combine things. So what we'd like to be able to do is put together my birth as two words and have a meaning for that phrase, a meaning for the phrase country, and keep on calculating up and get some meaning for the whole phrase, which we could then represent in the vector space. Okay, so if we build models of this type, we can potentially hope to do two things. We can potentially use them both as models that will build structure, that they'll actually build a sentence structure as they go, and they will also build semantics, that they will build a meaning representation for these phrases as they build up. So the general picture of what we're going to want to do is we're going to start off with a bunch of words and their word vectors, which we'll look up in a lexicon. The cat sat on the mat. And then we're going to start building phrase structure. So we're going to say, that's a noun phrase, this is a noun phrase, prepositional phrase, verb phrase, build a sentence. So we'll have a kind of a syntactic phrase structure over the tree, and then we'll, using that, kind of build up the semantic representations. And for that case, I just sort of knew what the right phrase structure I wanted for the sentence was, and just sort of drew in those nodes and calculated their semantics. And well, one of the questions is, how could we calculate that as we go along? And I'll come back to that in a minute. But before doing that, I just wanted to spend a couple of slides just sort of going back over the connections and differences between the model types that we've been looking at recently. So up the top half, we now have our tree recursive neural network. And in the bottom part, we then have our recurrent neural network. Now, in some sense, the kind of linear sequence models that you get for recurrent networks are kind of sort of like a limit case of a tree. So that if you sort of stare down from about this angle, what you're looking at actually looks like a tree, right? If you sort of tip it, it's sort of like this tree, but it's a tree that's always sort of right branching down to the right. And, you know, actually it turns out that quite a lot of English structure is right branching down to the right in most sentences, though you sort of get these pieces of constituency where you get left branching, like the country in this example. But if you look at the details of these two models, the details of the model are then kind of different, because in this model, we're exclusively sort of building upwards. We're taking smaller pieces of structure and then computing a representation for a larger piece of structure that they compose into. Whereas this model is sort of actually a kind of a funny sort of mixed model when you think about it, comparing it to a tree, because the sort of the word vectors are going up to compute something, but then simultaneously we have something going down the tree. And that's sort of the idea that Richard was mentioning last time, how the recurrent models are really sort of capturing representations of whole prefixes, and you're not getting any representations of smaller units than that. There are a couple of other pluses and minuses to think about. So the problem of tree recursive neural nets is that you have to get a tree structure. And so this is actually a huge problem. I mean, if I admit right at the beginning, you know, tree recursive neural networks have not swept the world. You know, there's some really good linguistic reasons to like them, and we'll say some stuff about them. But if you just sort of go out on archive and start looking at what people are using in neural networks for language, you have to look for a while to find people using tree-structured models, right? There's 10 times as much use of the LSTMs that we've talked about previously. And a big part of that reason is because to use a tree recursive model, you have to have a tree structure. And for some of the things that we've talked about, I think you can sort of immediately get a sense of why that's problematic, because putting a tree structure over a sentence is making deterministic categorical choices as to which words are going together to be constituents while other words aren't. And anywhere you're making categorical choices, that's a problem for learning a model simply by running backpropagation. And so that sort of puts complexity into these models. It also means that they're kind of GPU unfriendly, because there isn't just this sort of simple lockstep computation like an LSTM gives you. So LSTMs have this very simple structure, because it doesn't matter what the sentence is, the structure is always the same, right? You just have that same sequence model that chugs along them from left to right, which makes them very computationally appealing. But of course, they have the disadvantage that they're not actually representing any of the structure of the sentence. And, you know, if you want to get back to my original picture with the CMU bag of words, I think there's just sort of a manifest sense for human languages that if you just want to have the sort of first cut, roughly the structure of human languages right, what you're going to have is sort of know which subunits of words go together to have behave as constituents in the sort of the semantic parts out of which bigger sentences are described. Okay, so conversely, we can also think about the relationship between the tree recursive neural networks and convolutional neural networks. So the essential difference there is that the tree recursive neural networks calculate representations, compositional vectors, only for phrases that sort of make sense, that are grammatical, that a linguist would say is part of the structure of the sentence. Whereas what a convolutional neural network does is say, okay, let's just work out representations for every pair of words, every triple of words, every 4 words, regardless of whether they make any sense or not. But again, there's actually an advantage to that, right? That since you're not actually having to make any choices and you're just doing it for every pair of words and every triple of words, you don't need a parser. You have, again, you're back to this sort of uniform computation without any choices. But, you know, it's not very linguistically or cognitively plausible, I feel. You know, to some extent, I actually think recurrent models are more cognitively plausible as an alternative to tree-structured models than convolutional neural networks are. So the sort of picture is that for, you know, the CNN, you're sort of making a representation for every pair of words, every triple of words, every 4 words, whereas the tree recursive neural network is saying, well, some of those representations don't correspond to a phrase, and so we're going to delete them out. So that for the the convolutional neural network, you have a representation for every bigram, so you have a representation for their speak and a trigram, their speak slowly, whereas for the recursive neural network, you only have representations for the sort of semantically meaningful phrases like people there and speak slowly going together to give a representation for the whole sentence. Okay, so how do we go about calculating things in a recursive neural network? So the idea is when we want to build a representation of a larger unit, what we're going to do is take the representation of its children, and we're going to have sort of binary trees for what we're showing here. We're going to stick them through some kind of neural network, and we're going to have probably two things come out. One is going to be a vector that's representing what is going to be the meaning of this larger unit if you construct it. But if we'd also like to parse at the same time and work out good structures, we also want to have some kind of score as to saying, is this a good constituent? Because that will allow us to build a parser at the same time. So how might we do that? If we sort of start doing it the simplest way possible, just using the kind of rudimentary neural networks that we've looked at, this seems like the kind of idea of what we could build. So we could take the vector representations of the two children, which might be just words or might already be phrases that you've built up. We could concatenate them to make them into a bigger vector, have a linear layer, multiply by a matrix, add a nonlinearity, put that through a tanh, and so we've just got the simplest kind of single neural net layer, and that will then give us our representation of the parent. And then we want to score that, and well, one way we could score that is just having a vector here that we can then multiply this representation by a vector, and that'll give us a score for a phrase. And doing precisely that was the first type of tree recursive neural network that Richard explored in his work back in about 2011. Okay, but if we have just this, then we're in a position where we can use it to parse a sentence with a tree recursive neural network. And so the easiest way to do that, and it's kind of similar in a way to what we did with the dependency parsers sort of 3 weeks ago, is to say, look, what we're going to do is we're going to run a greedy parser that we're going to look at what seems best and make hard decisions on each action and then proceed along. So what we could do is we could start off with the sentence, the cat sat on the mat. And what we're going to do in a sense is kind of like what the first part of a convolutional neural network does. We're going to take each pair of words and we're going to calculate a representation for that pair of words. But we've got one other tool at our disposal now that we're also calculating a score for these combinations. And so we can say, well, the thing that scores best as putting together a phrase is these two words on the left. So why don't we just hard commit to those and say, okay, we've got the cat as a constituent with this semantic representation. And so then at that point, we can, for what to do next, we have all of the choices that we had before. And additionally, we have a choice that we could put the cat together with sat. So that's a new choice that we can evaluate. And at this point, we can say, well, it looks like the best thing to do is to combine the mat together, because that's got a good score. So we do that, and we commit to that. Then we've got one new thing we could try, because we could have the mat go together with on, and we can look at that, and we could say, oh yeah, that's a really good thing to do. On the mat, that's a really good phrase to have found. So the neural network will commit to that one. And then we'll kind of keep on repeating, and it'll decide putting sat together would be a good idea. Sat on the mat, that's a predicate. And then we'll combine that together with the cat, and we are done. And so we're sort of greedily, incrementally building up parse structure as we go along and working out the parse structure of the sentence. And so at the end of the day, that's a parse tree, and we're going to have a score for our parse tree. And that score for the parse tree, we're just going to say we've got a score for each individual decision as we put two nodes together, and the tree's got a bunch of nodes in it, and we're just going to sum those scores of each node decision, and that will give us a score of a tree. And what we'd like to do is find the very best tree for this bunch of words, and we've kind of approximated this by sort of doing this greedy algorithm where we just committed to what looked like the best constituent to build at every particular point in the time. And so the final thing was then sort of set up as a loss function with a sort of max margin objective where you're sort of trying to adjust the parameters of the model so that you're maximizing the scores of the sentences that you have found, and then you're considering what the sort of structures you were finding, what incorrect decisions you'd made versus what the gold structure for the sentence is meant to be in the sort of gold structure in a tree bank that tells you what the right answers for it. And in this kind of a model, you're sort of, in theory, what you'd like to do is find the best tree for each sentence according to your model, and then be changing the parameters of the model so the model thinks that the best tree is the correct tree in the tree bank, and that's then going to be minimizing your loss. In practice, finding the best tree according to your model can require an exponential amount of work, and we can't do that. And so we're just substituting in this greedy finding of a parse that looks sort of good according to our model, and using that in our loss function right here, the sort of the score of the parse that we found. There are obvious generalizations of this. Rather than sort of keeping just one greedy best parse that you're finding, you could have a beam parser, and you could explore some different possibilities, and you could sort of have a 10 best beam and sort of explore a bunch of parsers to the end, and sort of then come up with a better estimate of what is the best parse according to your model. But the central thing to be aware of as to what you can't do is the standard result for parsing context-free grammars, when you have grammars with labels like noun phrase, verb phrase, and things like that, that what you can do is dynamic program context-free grammar parsing, and so you can then do parsing of context-free grammars in ON cubed time and be guaranteed to have found the optimal parse for your sentence according to your grammar. The problem is, here, every time we're putting together two constituents, we're running it through a little neural network, and we're getting a vector up here. And so for any way of putting things together differently, we're going to get different vectors up here. And so there's no substitute that if you were actually wanting to guarantee you'd found the best parse of a sentence, that you'd have to do the exponential amount of work of exploring every different possible way of putting things together, which we don't want to do, but in general you can work pretty effectively by sort of doing fairly greedy exploration informed by your model to find good structures. Okay, so this is our overall objective function, and we want to be changing the parameters of our model so that it's wanting to choose as its parse of the sentence the one that's the same as the gold parse of the sentence. And so the way we do that is, again, by a backpropagation algorithm. So we'd sort of, for the recurrent neural networks, we had backpropagation through time, where you're sort of chugging back through the time steps of your linear model. You can generalize that to tree structures, and actually that was done by a couple of Germans in the 1990s. Goller and Küchler then came up with this algorithm called backpropagation through structure. And in principle, it's the same as the backpropagation we've seen again and again and again, but it's sort of just slightly more complex because you have to be getting things working over a tree structure. So it sort of ends up that there are three differences. So for working out the kind of updates to the matrix W in your neural network that sort of just like an RNN, you're going to be summing up the derivatives of the sort of error signals that you get coming into W everywhere you see it inside the tree structure. Something that's slightly different when you backpropagate down is since you're backpropagating down a tree structure, you then have to split the derivatives and send them down both branches of the tree structure to the next level below. And then when you're calculating your error messages, you'll have an error message coming in from the node above. You want to be adding to it the additional error from the node itself, and then you want to be splitting it and passing it down to the two nodes down below you. In these slides, there are then some slides that go through that in more detail, summing derivatives of the nodes, splitting the derivatives at each node, add error messages. And actually, from Richard last year, he wrote some Python code for doing backpropagation through structure. I thought I wouldn't actually try and explain in any more detail than that in class right now, all the details of that, but you can look at these slides on the website and chug through it in more detail than that. And I thought we could skip straight across to Kevin, who's going to be doing today's research highlight.
Okay, hi everyone, I'm Kevin and I'm going to be presenting deep reinforcement learning for dialogue generation, which is a paper by some people here at Stanford, but some people elsewhere as well. So the goal of this paper is to train a chatbot that can hold a reasonable conversation. And the authors approach this task in the sequence-to-sequence framework, where the input sequence consists of a message or perhaps several messages from a conversation, and the output sequence is a response to the message, and that's what the chatbot will say. So they use the exact same encoder-decoder model you saw for machine translation last week, and they use you can train this model with the exact same training objective, which is maximum likelihood estimation. So you find a data set of people talking to each other, and you train the model by making it assign high probability to the responses people say. So once you've trained a model like this, it's kind of fun to have the model talk to itself and see what happens. So this is a real conversation from the model in the paper. So the first chatbot says, "How old are you?" And then the second one says, "I'm 16," and the first one says 16. And then things kind of fall apart. So the second chatbot says, "I don't know what you're talking about." The first chatbot says, "You don't know what you're saying," and the chatbots get stuck in an infinite loop. So if we look over this dialogue, we can sort of point to some problems that might be causing this issue. The first one is actually the response, "I'm 16," although it's kind of a reasonable follow-up to the question, it's not very helpful. So it'd be maybe better to say something like, "I'm 16, how old are you?" And now you're giving more guidance to your conversation partner on what you should say next. The second issue here is this "I don't know what you're talking about" response, which actually is more or less a reasonable reply, like it still kind of makes sense, but it's a very generic response. And really, the main issue here is that we're training our model to produce sentences that have high probability, but that actually doesn't necessarily mean sentences that are good and useful for the conversation. So with the "I don't know what you're saying" example, it is high probability because really, no matter what you say to me, I can respond with "I don't know what you're saying," and it sort of makes sense. So trained with maximum likelihood estimation, the model thinks, great, this is a good response, and we want some different objective to train the model. That got a little bit messed up, but the criteria we could think of for training a good response is that it is reasonable, so it makes sense, but also that it's non-repetitive, so we don't get in an infinite loop, and that it's easy to answer, so you say something a little bit more helpful than just "I'm 16. And in this paper, the authors come up with ways of computationally scoring a response according to these criteria. So they end up with a single scoring function that takes the response as input and returns some number indicating did we do a good job with this response or not. And then they train a model to maximize the scoring function using reinforcement learning. So I'm not going to go into detail on how reinforcement learning works, but the main idea is that instead of learning from an example, so how a human responded to a message, you learn from a reward signal. So we start off with, as before, encoding the message in a vector. But now instead of passing in a human-generated or a response that a human said and trying to increase its probability according to the model, we're going to just leave the model to its own devices and have it produce a response, and then give it a reward signal which tells it, did it do a good job with the response or not, which is that scoring function I mentioned earlier. So here it's negative because I don't know is a good response. And through reinforcement learning, the model will learn to not produce these poor quality responses. So now on to some results. How well does this work? These first results are quantitative results where the authors showed dialogues produced by this system to humans and had them say which of these dialogues were better. Here a positive number means the reinforcement learning system did better. So you can see that humans thought that the reinforcement learned system was better, particularly at making messages that are easy to answer and also for the general quality of a several turn dialogue. We can also have our chatbots talk to each other again. And here you see that it's doing a bit better. So the first chatbot asks, how old are you? But now instead of saying, I'm 16 only, it also says, why are you asking? So it's kind of helping the conversation move along. But actually, after a couple turns, they end up in the same infinite loop. So this just kind of highlights that although reinforcement learning is a useful technique, it doesn't kind of magically fix everything. So to conclude, reinforcement learning is helpful when we want our model to do something beyond just mimicking the way humans perform a task. And it's been applied to many areas beyond dialogue. So if you're interested, there's a lot of new and exciting work in that direction. Thank you.
Okay. Yeah, so we'll have a bit more reinforcement learning in this class, including, I think, next Tuesday. It might come up. But maybe I should just, while we're on that topic, advertise that our newest Stanford CS faculty, Emma Brunskill, started work yesterday. And in the spring, she's going to be teaching a class on reinforcement learning. So if you want to get a good dose of reinforcement learning, there's an opportunity there. Okay. Yeah, so what I wanted to do now was sort of show you a bit more about how we develop some of the ideas of having these tree recursive neural networks. I guess I haven't really shown anything in the sort of quantitative results of show big results tables for that simple recursive neural network. But the summary of it was that, you know, we could do some sort of useful things with it for learning about paraphrases and getting syntactic structures right. You know, it sort of worked, able to publish a paper on it and all of those good things. It seemed like it wasn't really fully adequate for doing all the things that you wanted to do for understanding sentences and semantic composition. And there are a couple of ways in which that was true, it appeared. And so for some of the later work, and only some of which I'm going to be able to show you today, we were then sort of starting to explore better ways in which we could put sort of more flexibility or better neural units into this sort of same basic model of tree recursive structure to be able to do a better job. And there are sort of a couple of ways in which it seemed like the model probably wasn't doing what you want. The first one, the no interaction between the input words, is I kind of think a common issue that happens with quite a lot of models if you just have a single neural layer. We sort of mentioned this also when we were talking about attention, that if you just sort of concatenate C1 and C2 and put them through a single matrix multiply and then a nonlinearity, that you can think of the weight matrix as sort of being just segmented into two smaller matrices, where one W1, say, matrix multiplies by C1, and the W2 matrix multiplies by C2, and then you just sort of do the element-wise nonlinearity, which sort of means that the two words, their meanings don't actually really relate to each other. And that sort of seems bad, and I'll come back to that as the sort of last thing I touch on today. But before we get to that one, the other thing that seems kind of dubious here is for all semantic composition, we just have one composition function which has one matrix. So it doesn't matter whether we're putting together an adjective and a noun, or a verb and its direct object, or even if we're putting together the rest of a sentence with a period at the end of it. In every case, we're using exactly the same matrix multiply and saying, just multiply by that matrix and that'll put together the meaning of your sentence for you. And that seems pretty wishful when you think about it. And so an idea that seemed a kind of a neat idea was, could we get something more powerful by allowing more flexibility in the composition function for different kinds of syntactic constructions and their composition? And so that led to the idea of syntactically untied tree recursive neural networks, which actually proved to be a very successful idea for building high-quality parsers that parsed very well. And essentially what this model did was sort of argue that there's a reasonable separation that can be made between syntax and semantics in the following sense, that there's sort of basic syntactic structure of languages. So you have a noun phrase which can have a smaller noun phrase followed by a prepositional phrase like the man at the lectern, and the prepositional phrase will be a preposition followed by a noun phrase. That kind of syntactic structure can be pretty well captured by actually a symbolic grammar. So we assumed in this model that we did have a symbolic context-free grammar backbone that was adequate for basic syntactic structure. But the problem for sort of traditional NLP and linguistics is, although such a backbone is pretty adequate for telling you the possibilities for building syntactic structure, it's not very good at working out which structures that you should build or what is the meaning of different kinds of units. So the suggestion is it's perfectly fine to use discrete categorical structures for the syntax of a language, but what we want to do is make use of our soft vector representations for describing the meanings of languages. And so therefore we can sort of start with that observation and then build the kind of flexibility of composition that we're wanting by saying, well, if we are sort of knowing about something about syntactic structures in a categorical way, if I walk right over here, well, we can know the categories of the children. So maybe this is a preposition and that's a noun phrase. We can use our symbolic grammar to sort of then say, okay, these will go together into a prepositional phrase. And so since we know these categories here, we can then also use those categories to decide a composition function. So we can decide, okay, we're composing together a preposition and a noun phrase. So let's use the composition function that's the right composition function for putting together a preposition and a noun phrase. And so here now on this side, rather than just always using the same W matrix for any cases of composition, now we can say, let's use the W matrix for putting together a preposition and a noun phrase, and that'll give us this bigger unit, which will have some category according to our syntactic grammar, and then we're going to be putting together an A and a P1, and so we'll be able to use the right composition matrix to put together those categories. Yeah, so, and there are some other good properties of doing things this way from a practical sense. Doing simple PCFG parsing with a categorical grammar is fast because we can do it just using the symbolic categories and dynamic programming. And then we only have to be doing the sort of deep learning on the structures that we know are the ones that we want to build. So it's actually we are using syntax to guide what we build rather than trying out every different way of putting pairs of words together. So essentially, we're using the syntactic model to work out, reasonably plausible structures for the sentence, and then we're building the semantic combination for those structures, and then using the semantics to do the sort of harder decisions as to what does this prepositional phrase modify and things like that. And so we called this result the compositional vector grammar, where it was a combination of a probabilistic context-free grammar plus then using this tree-structured recursive neural network grammar. And in this class, we haven't really talked about sort of the whole history of doing parsing for natural language processing and the kind of grammars that people built. But in some sense, you can think of this as a generalization of the kind of things that people have been involved in for the last decade for trying to improve the quality of parsers. So the starting point is you can just have a context-free grammar parser, and that works very badly for natural language because you kind of can't do a good job of dealing with all the syntactic ambiguities and deciding things like prepositional phrase attachments. So back in 2003, Dan Klein and me sort of said, well, if we did some manual feature engineering and we kind of split categories and we had fine-grained categories, and so that we knew it was not just a prepositional phrase, but a prepositional phrase headed by of or a prepositional phrase headed by for, we could actually just have a CFG parse quite a lot better. And that was true. Then following on from that, a few years after that, Slav Petrov said, well, maybe we could actually learn those subcategories automatically, and that could help things along, and that did work. And simultaneously, there was a whole line of work on doing lexicalized parsers, which sort of said, well, a reasonable way to represent the semantics of a phrase like the person at the lectern is to say what is the head word of that phrase, it's person, and just represent the semantics of the person at the lectern with the semantics of person. And that was a useful idea to help parsing and making disambiguation decisions, because to some extent that's right. But on the other hand, you're losing a lot because you're saying that the meaning of the person at the lectern is just person, and you've lost all the other words of the at the lectern. And so effectively, for the CVGs, we're trying to sort of extend that further and saying, well, no, rather than just having a sort of a finer-grained syntactic representation or substituting in the head word and using it as the semantic representation, we can actually calculate a semantics, a meaning for the whole phrase, and then use that for doing our disambiguation decisions in semantic parsing, and that will be able to be more accurate. And to a first approximation, that actually works. So here are some results from parsing. So this is sort of trying to parse for context-free grammar structures, natural language sentences over a famous corpus of Wall Street Journal articles. And what we're scoring here is sort of an F1 measure as to whether you're getting particular constituents right. So you're making constituency claims like that there's a noun phrase from word 3 to 12, and then that's either right or wrong. And so you can see how there's been a succession of people gradually getting better at this task. So if you just sort of have a plain CFG, your score is about 72%. So our more kind of manually feature engineered context-free grammar was considerably better, about 85%. Some of the ideas of having putting in lexical heads were even better, 87%. The automatically splitting, which sort of mixes syntax and lexical information, was even better at about 90%. And if you just have a plain RNN, it's sort of not that great, because if you only just have one W matrix, you kind of can't model a lot of composition. But by having this idea of the syntactically untied RNN, where you could learn these different composition functions for different kinds of phrases, that actually worked very nicely and produced a strong, well-performing parser. I mean, there are some better parsing numbers where people have done various kinds of self-training and data augmentation, and actually there are some more recent results since 2013 that I don't show in this slide. But nevertheless, this sort of proved a successful way to sort of build a sort of more semantically sensitive parser. But in some sense, the interest of this isn't sort of just that it can get parse structures right for sentences. Really, the biggest interestingly different thing here is, well, actually, we are computing a semantics, a meaning representation for each phrase, that gets back to that original idea of understanding meaning similarities. And that's just something that by itself, the sort of context-free grammar isn't giving you at all. And there's sort of some neat things that you can see out of that. I mean, one of the neat things that you can see out of this is just sort of, you can observe how the soft grammar learns notions of where the information is, and so what are head words of phrases. So this is as it sort of starts to put together pairs of words that you can see by the activations in the matrix as to where it's getting information from. And so there's something you have to know to interpret this. So for training this model, what Richard did was he started off the matrices with sort of identity initialization, but they're sort of kind of two half matrices with identity initialization, because this is sort of the part of the matrix that's multiplying the left child, and this is the part of the matrix that's multiplying the right child. So they were initialized with identity initialization, as we've sort of spoken about before. That sort of has a similar effect of allowing this sort of propagation of information at the beginning of training to the kind of thing that an LSTM does. And so if you're putting together a noun phrase with a conjunction, so this is sort of something like the student and, well, it's correctly learning that most of the information is coming from the student and there's relatively little coming from and. If you're putting together a possessive pronoun and the rest of a noun phrase, so it's something like his cat, most of the information is coming from cat with relatively little coming from his. And here are some sort of other examples. If you're putting an adjective together with a noun, so this is something like red chair, it's learning that you're getting kind of quite a lot of information from both sides. This is a whole adjective phrase and a noun, so this is something like extremely dark movie. So you're again getting lots of information from both sides. And there's sort of some structure here that you can sort of see the same dimensions seem to be marking the kind of modifier meaning for both the adjective phrase and just the plain adjective. So that's kind of cool. The more interesting thing then is to sort of say, well, are we actually getting sort of a semantics for these phrases and sentences that is capturing semantic similarity in the way I claimed right at the beginning? And actually that did work reasonably well. So here's one sort of test that we did to try and illustrate that. So basically we're saying, okay, for any sentence or any phrase, we've calculated a meaning of that phrase that we can sort of place into our vector space. So just like for word vectors, we can then say, what other sentences are placed nearest together in the space, because they should have the same meaning. So if the test sentence is all the figures are adjusted for seasonal variations, the two closest other sentences in the Wall Street Journal corpus, well, all the numbers are adjusted for seasonal fluctuations, all the figures are adjusted to remove usual seasonal patterns. And this is kind of actually nice, right? Well, in some parts, like all the figures, all the figures, they're the same, or all the numbers is very similar. But in other places, it seems to have learnt quite interesting things. So are adjusted for seasonal variations, are adjusted to remove usual seasonal patterns. So that's actually kind of quite a different piece of word choice and syntactic construction, but it's learnt quite nicely that they're very similar in meaning. Knight Ridder wouldn't comment on the offer. The two closest sentences were Haskell declined to say what country placed the order. 2, Coastal wouldn't disclose the terms. Those ones aren't quite so excellent, you could say. I mean, to be fair, I mean, something that you have to be aware of is that there are limits to how perfectly you can find other sentences that mean roughly the same thing, because this is only being run over a corpus of about 40,000 sentences. So except in sort of fairly formulaic utterances that get repeated quite a bit, you know, you aren't often you're going to have to be choosing sentences that are sort of somewhat different. So, you know, there probably aren't other sentences with Knight Ridder not commenting on an offer. So, but, you know, some of them are perhaps a little bit too different. So, you know, declined to say what country placed the order. But nevertheless, it does seem to have captured something as to what the main semantics is going on. So all of these, so this first sentence is a company not wanting to say something about some transaction. And both of these two closest sentences are also a company not wanting to say something about some transaction. So there is a sort of a meta sense in which it does seem to have captured the semantic similarity pretty well. And then the final example here is sales growing, and again, the two sentences that are closest to that are both other sentences when sales are growing further. So that was kind of nice, and that still seemed to work pretty nicely. We still kind of weren't really convinced that we were doing a great job at capturing semantics of phrases, and there was still a worry that things didn't work very well. So now we'd changed things so that we had different W's depending on whether we're combining an adjective and a noun and a verb and its object or whatever like that. But, you know, otherwise, we still had the problem that I mentioned before that hadn't gone away, that when you're doing this matrix vector multiply, that what you're doing is you've still got kind of half of W as multiplying itself by C1 and half of W as multiplying itself by C2, and there's no real interaction between C1 and C2, and that just doesn't actually seem what you want for natural language. Oops. Okay, sorry. Yeah, that was a bit from we did before. And so, in particular, you know, what every semanticist has observed and worked to account for in symbolic theories of semantics for the last 40, 50 years is that what you actually get in natural language is that you have words that act as operators or functions that modify the meaning of other words. So that if you have something like very good or extremely good or quite good or any of those things, it seems like what you have is you have good that has a meaning, and then very is some kind of operator or function that will modify the meaning of good to make it sort of more extreme and strong or weaker, depending on whether you're saying very, extremely, quite, etc. So it sort of seems like somehow we'd like to be able to build neural networks that capture those kind of ideas of composition for language. And so the last thing I want to mention today is, you know, this was sort of then version 3 of how might we capture that composition. And so essentially, if you have a vector here for good, and then you want to be able to modify its meaning with an operator like very, and how might you do that? Kind of a natural idea from sort of linear algebra to think about is, well, what if I made very a matrix? Then I can do a matrix vector multiply and calculate a new vector, and that could be a meaning of very good. And there had been some previous work that sort of for particular just phrase combinations had done precisely that. So there had been a paper or two that looked at, let's describe the meaning of adjective-noun combinations or adverb-adjective combinations by doing that kind of matrix vector multiply. But we wanted something more general that could be applied to whole sentences arbitrarily to come up with a meaning. And so this came up with a model where sort of we were going to have matrices and vectors, and we were going to combine them together in all ways to try and create sort of meanings for phrases. So if we now had very good, what we're going to say is, well, we're not quite sure when something's going to be an operator and when it's going to be operated on. So let's just have it both ways and see what comes out. So for each word, it's going to be represented by both a vector and a matrix. So very and good are both represented by a vector and a matrix. And so then to compute a representation of the phrase very good, what we're then going to do is we're going to multiply the vector by the matrix, so big A with little b, and we're going to multiply big B by little a, and so we're going to do both vector matrix multiplies, and then having done that, we're going to concatenate those together as before, and then we're going to multiply it, put it through a neural network layer just like before, so we have another W matrix to decide which of these to use and how, goes through a tanh, and that gives our parent representation. And so at that point, we've got a vector representation for the parent. And that sort of looks hopeful, but well, we want to keep on building this up into a representation of whole phrases, and we want to be able to build very good movie. And well, at that point, we sort of conceptually want to be using the word vector for movie, and we'd like to say, well, this is another operator, and we'd like to multiply very good by movie. So to do that, we're going to have to also have a matrix coming out for very good. And so we wanted to build one of those. And so we said, well, in addition to that, what we could do is put together the two matrices A and B that we got down here. We could concatenate them to build a bigger matrix and do a matrix multiply on that, and that would then give us a representation as a matrix representation of the parent. And so formally now, our parent will now have both a vector and a matrix. So I'll show you a bit about this model. It was, it could do some quite interesting things, and it also had some weaknesses. And I think in terms of where the weaknesses are, if I give the game away right at the beginning, a lot of the weaknesses were in this part here for the matrices, because we sort of had problems with that. I mean, firstly, the matrices were kind of problematic because matrices have a lot of parameters in them, and so that makes it hard to learn them effectively. And that's an idea that could perhaps be revisited using some ideas that have come up since then. But secondly, we didn't have a very good way of composing matrices to build bigger new matrices, so that part of the model perhaps wasn't so great. But here's sort of a picture that sort of shows you some of the things that you would like to be able to do and whether models can do them. So we're looking now at building two-word combinations. So fairly annoying, fairly awesome, fairly sad, not annoying, not awesome, not sad, unbelievably annoying, unbelievably awesome, unbelievably sad. And then what we're wanting to do is take those phrases and interpret their sentiment and put a probability distribution over sentiment scores between 1 and 10. So 10 is extremely good and 1 is extremely bad. And for some pairs of words, we actually had some sort of empirical data that was kind of connected to these meanings. The empirical data was kind of a sort of a distant supervision, not to be trusted very much, but this was sort of saying, well, suppose we'd seen a review of a movie that said not sad in it, what rating was being given to that movie, it was sometimes a bad rating, occasionally a good rating, and that sort of was shown in that one example for the red line. But, what's perhaps more interesting to see is that, for some of these combinations, that the plain RNN is actually more effective than you might have thought at first it will be. So if it's something like unbelievably awesome, that can be captured pretty well, and the model captures that unbelievably awesome, that even the basic RNN model is good at knowing that means it's a very good movie and very positive sentiment. It can even do some sort of more interesting things. So if you have the phrase unbelievably sad, it turns out that that's kind of ambiguous, that there are many really good movies that are unbelievably sad, so there's a lot of weight over here. And then there are some cases where people say a movie is unbelievably sad because it's just terrible. And so you're actually getting this sort of U shape where you get some weight on both ends of the spectrum. And interestingly, even the plain RNN and also our matrix vector RNN is able to capture that pretty well. And so that's kind of nice. But there are some things that the basic RNN just isn't able to capture right, where our new model does a lot better. So if you look in these middle row ones, like not annoying and not awesome, that by itself, the word not just tends to be a marker of negativity, right? People who go around saying not a lot, negative people. So all else being equal, if you see the word not in something, sentiment is more likely to be negative. And then the word like annoying, that's a negative sentiment word. And so for the basic RNN model, if you put those together, they just have a kind of additive effect, it turns out. So that's the green line, where if it says not annoying, it predicts that means bad movie, low rating. Whereas the result we'd like to have is that not is an operator, and it modifies the meaning of annoying, and it means like it's not so bad, it's not annoying. And the interesting thing about natural languages is that they sort of don't work like sort of basic logic, where basic logic might tell you that not annoying means this is a good movie because it's not annoying, where real human beings, when they say words like not bad or not annoying, they mean it's sort of okay. And so the distribution that the matrix vector model comes up with is sort of flat, but it's sort of at least basically right, that it actually gives the highest probability to the mid-range of the distribution, which is kind of correct. And you see a similar effect with not awesome, that the basic RNN isn't able to capture that. It's still giving most of its weight to saying, I've seen the word awesome, this is a good movie. Whereas the matrix vector RNN is at least done sort of better, and it's tamped down, giving weight to meaning that it's a great movie. So it sort of seems like we're kind of doing better at being able to model sort of meaning combinations. Yes?
W matrix is already based on the syntactic rule. Can the syntactic rule also tell you which direction to apply? Okay, so the question is it really wise to be doing it both ways with the matrix and the vector, or could you actually use your syntactic structure and know which way to apply these two things and do it only one way? Yeah, so these result, even though all my phrases have the operator on the left and the thing being modified on the right, this is sort of running that symmetric matrix vector model, and it's just doing it both ways. So I think you're totally right. It wasn't something we did in this work, but it seems like you can very reasonably say, well, wait a minute, why can't you take both of these two models that you've just shown us? If you're using the sort of syntactically untied model, you know that if you're doing an adjective
noun combination, you should treat the thing on the left as the operator, and then you could just run it in one direction. And I mean, in general, I think that would be a very reasonable thing to try. I mean, it sort of means that you have to have complete coverage, and so you've decided in every case of when two different categories come together, you have to have decided for sure which is the one you're going to treat as the operator, and you know that might actually require quite a bit of work to do, but in principle you could do it and that would work. Yeah, so I've just, we're basically done for today, but just show you sort of one other thing that we were able to do with the matrix vector model, which was sort of a nice example of how we were able to use this model to do an NLP task. And so this was a task of learning semantic relationships as a kind of a relation extraction task. So this was a data set that some people had explored where you had sentences like, my apartment has a pretty large kitchen, and then what you were meant to say was, what is the relationship between apartment and kitchen? And there were a set of relationships that they could have, and one of them was a component whole relationship. And so the correct answer here was to say that the kitchen is a component of the apartment, and then there were various other relationships. It could be a tool that you were using, it could be the material something was made out of, and various other kinds of relationships. And so we explored using this matrix vector recursive neural network to learn these relationships. And so the way we were doing that is we were sort of building up semantic compositions using the matrix vector RNN model. And so we'd build up these semantic compositions until you reach the point where the two noun phrases of interest join together in the structure of the sentence. So the movie showed wars, so that this was the sort of the message, the content that's being shown on this media. So where they join together, we'd say, okay, we've built up a semantic representation that covers the movie showed wars. So at this point, we'd then use a neural network that's just a straight classifier that says, okay, classify the relationship here. It's an example of message topic. So we built that model, and this is sort of a nice example where it seemed like we were able to show that, again, sort of having this extra power gave us extra power. So here are just some results on that. So people had worked on this data set previously, so sort of a basic support vector machine, got about 60% F1, maximum entropy model, sort of so like a logistic regression model with a lot of features, got 77%. An SVM model with a huge amount of hand-built linguistic resources and features. So this is sort of using everything. It's using WordNet dependency parsers, Levine verb classes, prop FrameNet, Nomlex Plus, Google Ngrams, paraphrasers, text runner, every feature and knowledge source you could possibly think of to throw into it, got 82.2%. So here are our results with our neural network model. So the plain, recursive neural network got a little under 75%. So that's actually pretty good when all it's doing is learning its own semantics, representations that puts things together, but you know, not quite winning the pack. So the matrix vector model actually is clearly doing something useful. So it's sort of getting you about 4% better scores. So that sort of shows we have made some progress in semantic representation. Of course, like everyone else, we wanted to have our model better than the last people's model. So we then sort of built a model that sort of put in a few semantic features, but only, a few extra features, but only fairly basic ones, WordNet part of speech and NER, and that was sort of able to push us just over the line. But you know, I think the main message is that you're sort of starting to get decent semantic models of phrase relationships without actually having much more than just these continuous representations of semantics. Okay, I'll stop there for now, and we'll get to more next week.